Okay, hi everyone. Thank you for coming. I'm Sourav. Today I'll talk about our paper generating distributed randomness using something called weighted VRFs. This is a joint work with Benny, Aline, and Jolun from Aptos Labs. So let's get started. So we'll start with the problem definition. So this talk is about randomness beacon and what these are. So we can imagine a trusted ideal functionality that has a clock in it, and we have a set of recipients, and this ideal functionality is supposed to output random values at periodic intervals. So it will output R1, and then after some time it will output another value, so on and so forth. Okay, so this is what we want to implement eventually. And there are many applications of randomness beacon. In general, you can anywhere you want randomization, you can use it. Randomized theory, consensus protocol has a lot more applications. Clinical trials, digital lotteries, team drafting, player drafting. But this session is about blockchain, so this randomness beacon also have application in blockchain. For example, we can use it to protect from MEV. Leader election you have seen, and also games and lotteries. These are popular use cases of blockchains, and also NFT minting and airdrops, and possibly many more. So what we want from randomness in blockchains, so what we want is we want fresh randomness for every block. That's how we want to use in randomness in blockchains. So let's say we have a blockchain running, then for every block, we want a fresh coin. For B1, we want R1. And when we generate another block, we want fresh randomness to be able to use it for all sorts of applications that I've described. Okay, but a crucial point is, what is a good time to reveal these random values? So let's consider this line as our time, and where I'll specify where things happen. Let's say this is the time point where validators will commit a block, and we can reveal the randomness at various different point in time. But if we reveal the randomness too soon, let's say before the block is committed, then we give adversary the flexibility to change its mind and change the block. But if we reveal it too later, then it will halt the pipeline, blockchain pipeline, and you cannot do stuff until the randomness is out. So ideally, we want to reveal things simultaneously. As soon as the block is committed, we also want to reveal the randomness as well. We can get this property in certain scenarios, but I'll show an example where we have one additional message delay between the block commit event and also the randomness reveal event. Okay. So one approach to get randomness in blockchain is to rely on external coins. These are called coin oracles. And we have some examples like DRAND and Chainlink VRF, which are coin oracles. So given a coin oracle, this is how we can use randomness in blockchain. So after we create a block, we'll query the random oracle, we'll query the coin oracle and get the random value, and we'll do this process for every block. Okay, this can work fine, but it has issues. One security issue is that now we internally rely on the security assumption of the coin oracle. And the other issue is the usability issue is this. If you rely on an external source, then it's hard to get the timing really right, because as I have shown, we cannot reveal it too early or we cannot reveal it too late. So what we want to do is we want the blockchain validators to implement their own randomness beacon. So, and this paper is about how do they implement this randomness beacon. Okay? And to do so, we will rely on a cryptographic object. Those are called verifiable random functions, and we will use a threshold variant of it because distributed systems go very well with threshold cryptography, and that's what we will use. In this talk, there are various different cryptographic primitives like verifiable unpredictable functions or unique signatures. I won't make any distinctions between them, but treat all of them as verifiable random functions. Okay, let's see how to design a randomness beacon given a threshold verifiable random functions, or VRFs in short. Okay, so VRFs will rely on threshold secret sharing. These are parameterized by n and t. These are very classic primitives. So here the idea is we have a secret S, and we want to partition the secret into n pieces such that any subset of t plus 1 pieces reveal the secret, and subset of t or less shares doesn't reveal anything about the secret. And this is one classic example of secret sharing you might have seen. This is also known as Shamir secret sharing, where we embed the secret as the constant term of a polynomial, and each share is just one evaluation point on the polynomial. So we will use this threshold secret sharing crucially. So I'll now talk about one classic example of a threshold VRF scheme, which is also known as BLS threshold signatures. So this is how it works. So parties will run a key generation algorithm to get some secret keys. Here S1 is a secret key, so each party will get a secret key, and the secret keys are a secret share, Shamir secret share of a random secret S. Okay, and there are some additional information that are not so relevant here. We can either rely on a trusted key generation to output these correlated secret keys, or we can also do a distributed key generation. Okay, now we have parties with signing keys that they somehow got, and the VRF computation is as follows. Each party VRF takes an input, which is the message here, and they'll just compute sigma I, which is hash of the message raised to this individual signing key. So you just have to think of this as some deterministic operation that every party computes. So each party will locally do that, and then they send this sigma I values to an untrusted aggregator. An untrusted aggregator somehow combines them to get this term rho. And we use rho as the VRF output. So this is to compute rho, you need to get you need to get at least t partial signature sigma. So that's why this is called a threshold VRF. So these are some really nice properties. So this is a signature scheme. So we'll talk about signature properties. So it has non-interactive signing. The partial signatures are also fast. The aggregation costs are also fast, and also the crucial property we rely here is that the signatures are unique. That's why we can use them as a VRF. Okay, good. So given a threshold VRF, how do we use them to get randomness beacon? It's very simple. So for the I-1 block, we just compute this fancy looking function, but this is nothing fancy. So we hash the block, we take the block hash and evaluate the VRF on the block hash. Note that VRF takes an input, which is the message. You can think of this hash of the block as the message. And then we use this output as the random coin. Okay, and we do this for each block. So now, because of the threshold property, computing this VRF requires at least t contribution from t parties. That's why we get the security. And it also, as I have shown, this only requires one additional rounds of interaction. So what security properties we need to get? We can get same security properties as the underlying blockchain if we run this VRF function, threshold VRF function, using the blockchain nodes. And in terms of usability, we just get one additional latency. So this is pretty good. But we are not done because I have some time. So what we need is we want randomness for proof of stake blockchains. And this is a slightly different problem statement because here the parties are weighted. So we have a set of parties or a set of miners, which are also known as validators. In a proof of stake blockchains, these parties will be weighted based on how much stake that they are contributing to the blockchain security. Okay, and the security assumption says, at most 1/3 of the stakes are malicious, and we need to solve this problem. So okay, before I go there, so staking is, for example, in Aptos, we have about 880 million staked by 129 validators, and we have these, the distributions can be arbitrarily different. So what we need to get a randomness beacon for proof of stake blockchains is we need a weighted VRF functionality. And this paper is about designing such a weighted VRF functionality. Okay. Before I go there, I'll give you a simple example of designing a weighted VRF, which is using a virtualization. Let's say we have parties with different weights, and then W plus is the sum of the weights. Then we can assign to each party signing keys proportional to their weights. And these will be secret shares using a very high degree polynomial. And the VRF evaluation will be each party will compute partial VRF outputs, which are proportional, number of VRF outputs proportional to their weights. And the rest of the step is very similar. So, but there are some issues, is that the per party VRF evaluation cost is now proportional to the weight. And also it requires aggregation cost, which is proportional to the total weight, and we also need a distributed key generation. So there are some lower bounds saying we cannot get all these properties in a very nice way. Also, we don't know how to get all the nice properties, but we only know how to solve one very well. 2 and 3 are still problematic, but we have some optimizations in the paper. Okay, so to design a VRF in the weighted setting, we have to start from a single party VRF. So the single party VRF works as follows. So we have some public parameters, which are G and H, which are some group elements. And the VRF has a signing key, a secret key. To generate the secret key, we sample a secret element S and compute the public key to be G to the S and secret key to be H to the S. And there is an additional step, which is called augmented key generation, where we sample a random value and compute some function of the secret key and this random value and publish this. This is called augmented public key. And this is nothing but H raised to S times R, because I'm multiplying R and S in the exponent. And there is a signing step, or the VRF evaluation step, which is hash of the message raised to 1 over R. And there's a derive step, which you can run to compute a derivation. So this is bilinear pairing operation. And the VRF will eventually look like this, but what is the intuition? So here, the augmented public key is an encryption of the secret key using a randomness R. And if you know what functional encryptions are, so we are doing something very similar there. And this partial VRF evaluation is a decryption key, which lets anyone with access to the decryption key to compute this final function, which is pairing of H along with hash of the message and raise it to the original secret key. So what we are doing is a functional encryption here. Very simple one. Okay, so if you know the BLS VRF, so our things look very similar. I won't go into the details, but we have this additional step where we are introducing an augmented key generation step that is not part of the original BLS scheme. Okay, so we talked about single. So this is about single signer VRF. So the rest of the talk, I'll say how to get a threshold VRF and how to get a weighted VRF. Okay. So the threshold VRF is very similar to the threshold VRF that we saw. So now parties will run a key generation algorithm which will output a secret key to each party and some public information. And the secret keys are H to the SI, where SIs are Shamir shares of a random secret S. So it's just a different encoding of the secret. That's how you want to look at it. Okay. If you remember the single signer VRF key generation, we sample a S and we compute secret key to H to the S. We are doing the same thing, but with a secret shared value. That's what we are doing here. And augmented key generation is also very similar. Each party samples a random value and computes this augmented public key by raising their secret key to this random value. So everybody will do this, and it's identical to single signer case. Okay. So now what's the signing step? So this is one of the crucial steps in our threshold VRF, is to each party uses hash of the message and raise it to 1 over Ri. Everybody will do this. And this is exactly identical to the non-threshold variant. So we are doing threshold variant, except parties are using secret shares of the secret key instead of the secret key itself. Okay? So the aggregation step is slightly complicated, but there are two crucial operations where the aggregator will take the partial signatures and compute some public operation, will do some pairing, and will do some multiplication. And eventually it gets this I won't go into here details, but eventually it gets a VRF output which looks identical to the single signer VRF. So what we did, we have a VRF scheme, and then we know how to thresholdize it very nicely so that it maintains the structure of the non-threshold variant. But well, we wanted a weighted VRF. So weighted VRF, it works as follows. We have parties with different weights, and they run a key generation algorithm, but the signing keys now it's proportional to this weight. So what we are doing here is virtualization. So we don't know how to solve this problem precisely. So if you want to make a note of it, you just have to observe how long is each value, and we want each value to be as short as possible, independent of the weight. But for the key generation, we don't know how to make them shorter. So what we are doing here is exactly virtualization. Okay. So the augmented key generation is where things become really interesting. So now each party samples one random value independent of their weight and computes this aggregated public key, which is as follows. They take their random value and raise it to the secret key. The party 2 will also compute these. So although the augmented public keys depend on the weight, but each party uses one random value independent of the weight. And that is the key point in our construction. So with one random value, the signing step is identical. See, the signing step is short. independent of the weight. And the aggregation step is also, again, kind of complicated, but you have to trust me that if I do this entire operation, I get a VRF which is identical to the single signer case. So what kind of properties we get? We get a non-interactive VRF computations, order 1 partial VRF size, also order 1 partial verification, and unique VRF output. So there are some limitations. We have aggregation cost, which is proportional to the total weight, and also the distributed key generation is virtualization based. So we did, this system is running on top of Aptos blockchain, and we measure this major macro matrix, which is how long does it take to run the distributed key generation and how long it takes to run the randomness beacon with different total weights. And the key takeaway is the randomness beacon is now very fast. We add a 200 milliseconds latency to get random values after the point when the block is committed. But the DKG latency is longer because of virtualization, but we only have to do it once every epoch, which happens to be 2 hours. And this is a very nice open problem to improve the DKG further. So I have some micro benchmark results. Is to compute a single party signing time, or the VRF evaluation time, compared with this baseline BLS virtualization that I have mentioned. Ours is constant, whereas the BLS is proportional to the weight. Also, we have constant verification time. It's better than the VLS. In summary, we design a randomness beacon in the weighted setting. So the core idea is to design a weighted VUF scheme with constant signature size. In the paper, we have many other things, including how to do this virtualization-based DKGs more efficiently using something called aggregatable PVSS. And we also have a full-fledged system that's running on top of the Aptos blockchain. And we prove the security of our scheme assuming this bilinear Diffie-Hellman assumption. There are very nice open problems. One is to improve the DKG, still in a virtualization-based. We have the secret key of the VRF, which is a group element. This is a little technical, but other cost is also improving the aggregation cost. Okay, that's all I wanted to discuss. Okay, thank you.
So I'm a little bit confused. So so you are saying that there's something that's still linear in the weight. And is it like the key size? Is that why the aggregation cost is still linear in the weight?
Yes. Yeah. The key. So what happens is we were doing. So each party reveals an encryption of a linear size signing key using the same randomness, and the signing key then the VRF evaluation is just de-randomizing the signing keys. So the aggregator takes this de-randomizer and de-randomizes a linear size message and then computes some function. So that's why we have a linear aggregation cost. Yes.
And the aggregation cost being linear in the weight is not because the signature is linear in the weight. It's because like the keys are linear in the weight.
Yes, it's because the keys are linear in the weights. Yes.
I have one question. So I would imagine there are certain scenarios happening on blockchain where a small group of people, they need some randomness. Let's say they want to play a game. Mm-hmm. So and I would imagine in such scenarios, it is possible that we don't have honest majority. So okay. I want to ask, is it possible that your technique can be extended to such scenarios with some non-trivial guarantees?
Okay. So what we are doing is that the protocol we design is client agnostic. So this is a randomness beacon that the validators are generating. So if clients wants to use a blockchain, they are inherently trusting the blockchain itself. And our randomness beacon trust assumption is identical to the blockchain trust assumption. So although there is honest minority among the clients, but they will be using a randomness value that the miners are generating, and the trust assumptions are identical there. Yes.
Okay, thank you.
Okay.
Yeah.
Yeah.
Yeah. Thank you.